Hi, everybody. Welcome to the talk today. So this is Jenny, who I've known for about a year and a half from our time at Georgia Tech. So she's currently a fourth-year PhD candidate, and she's going to talk a little bit about some of the work that she's been doing, covering some of the stuff in her proposal, as well as some newer stuff on the interface of robotics. So overall, she's co-advised by two different researchers. This is Dr. Erin Young and Dr. Greg Sawicki, and she'll kind of talk a little bit about that pathway. And then she's gotten a bunch of awards. So you've gotten like NSF JRFT, American Society of Biomechanics, some like travel awards and stuff. And then also, I don't actually know what the NSF NRT Arms Fellow is.
Research traineeship.
Research traineeship from Georgia Tech. So with that, take it away.
Thank you. Thanks everyone for coming. It's kind of fun to get here and talk to you guys today. And please let me know, I'm got a brief rundown of the background of everyone in the room and what some of you guys work on. So if there's anything that I'm talking about that doesn't make sense on a specific slide or something I should dive deeper into, feel free to throw your hand up and let me know. So today I'm going to be talking about kind of the overarching goal of my work, which is we're trying to make wearable robotics that can augment human stability during locomotion, so during walking. And to start off, Andrew suggested that I tell you guys a little bit about me and kind of my background before and leading up to grad school. So I was born and raised in the Midwest, in a suburb of Minneapolis, Minnesota. And then I went to the state next door at the University of Wisconsin-Madison, where I did my BS in biomedical engineering. I really started my whole research career at the Minneapolis VA hospital, which is a hospital for kind of veterans and military in the US. And this was a cool group because they did a bunch of different rehab engineering technologies, medical devices, exercise equipment, prosthetic legs, sockets, all that kind of stuff, and got exposed to a ton of stuff right away very early in my research career. And I was really interested in diving deeper into prosthetic limbs. So back at the University of Wisconsin, I joined the lab of a PI named Peter Adamczyk, and here I worked on, this is a variable stiffness foot. So as you're walking around, this is a prosthetic foot that replaces a foot for people who've had amputation. And as you're walking around, we can change the stiffness, and that kind of replicates the way that your foot naturally changes in different environments for people that do kind of have their healthy, intact limb. And we did a lot of stuff taking this out in different environments outside the lab, trying to figure out how does this need to change and adapt to different environments that our people are walking in. And this really got me into an idea that's carried through to my PhD, which is kind of bringing some sort of like intelligence and awareness to these devices, the context that you're walking in, how things need to change as you're moving. So the next internship I did was at the Shirley Ryan Ability Lab, formerly called the Rehab Institute of Chicago, or RIC, working with Levi Hargrove. And this got me exposed to all the wearable sensors, machine learning kind of approach to things. So they were trying to use a bunch of different muscle sensors on your upper limb to control a robotic hand prosthesis. So we were kind of testing that out in virtual reality and figuring out how you could use like pattern recognition based control to control some of these devices. And then lastly, I wanted to get a little bit of industry experience if I could during undergrad before starting grad school. So the big prosthetics manufacturer called Össur in Reykjavik, Iceland. And I worked on kind of a derivation of this top foot where we were trying to make something that was also kind of led into my PhD work a little better for diverse activities and kind of, you know, hiking, moving around, some of those things that require a bit more stability rather than just straight away running. And then I worked on a component for this lower foot. So I ended up landing at Georgia Tech for my PhD, where I'm in two different labs, very long acronyms for these labs. The Exoskeleton and Prosthetic Intelligent Controls Lab, or the EPIC Lab, with Dr. Erin Young. The focus there is really how can we bring machine learning into wearable robotics and make these devices that are really intelligent and kind of change with the person as they're moving around in different contexts, in different locations, things like that. And then the other one is the Physiology of Wearable Robotics Lab, and that's headed by Dr. Greg Sawicki. And on that side, we're trying to figure out if you put a wearable robot on someone, let's say it's offloading some of your limbs, like you can think astronauts that are in space for a while, kind of changes the way that your muscles and tendons are operating. So that side of the lab is trying to figure out if we're putting these wearable robots on people all the time, why are they working from more of a physiological, biological level? And how are we actually changing people's physiology as a result of wearing these devices all the time? So I'm about a year out or so from finishing my PhD, and also got my MS in mechanical engineering along the way when I was there. All right. So to jump in, kind of the brief introduction to exoskeletons is exoskeletons have showed a lot of promise in augmenting human motion, specifically human walking. And the big one that you'll see a lot in our field is lower limb exoskeletons. So these are wearable robots you wear on your hips, your knees, or your ankles. They usually have motors in line with your joints, or sometimes they're just passive devices. And the huge focus of this field really as it's been starting out, especially for these exoskeletons that are just at one joint rather than those whole lower limb ones you'll see for like rehabilitation with stroke and spinal cord injury, is in reducing the cost it takes you to walk. So this is as simple as, you know, if you go out and walk a mile, having you use less energy because you're wearing one of these devices. So all this is showing is that across the years here, so from 2009 to 2019, in 10 years, you can basically see this is the decrease in metabolic cost that these devices were getting you. So as it's gone on, we've gotten better and better at pushing kind of the cost of this down. And if you add a couple more years, there's one down at like -45 or something nuts. So there's really been a huge ton of progress on the energetic augmentation side of things. And then one of the other really big areas is in back and upper limb exoskeletons. Actually, one of these pictures that I'll show, Autobach is a German company that has some of the state-of-the-art upper limb exoskeletons. And this is really meant to kind of like offload weight that someone would be moving around on their own. So if you're in like a manual labor job and you're using your muscles to do these big heavy lifts or moving things or working kind of awkward, uncomfortable scenarios, I challenge you to stand with your arms like this for 10 minutes and see how tired your arms get, but that's a lot of like the automotive industry. And so this has been another huge application for exoskeletons. So one of the other things that we wanted to think about as we were moving into my PhD is in this context of people would be wearing these on a daily basis, other than just reducing your energy cost and possibly offloading some of this weight. What are some of the other applications that we need to be thinking about that would make people kind of get a lot out of these during daily use? What are some of the situations that people come across? So we really wanted to figure out how are humans moving in the real world and what are some different applications that exoskeletons could be used for. So this was a really cool study that basically tracked the number of steps in a row you take throughout the day. So you can imagine if you go to grab a cup of coffee, maybe you're walking down this hallway kind of straight away for 10, 20 steps, depending on where you are in the building. You stop, you're getting a cup of coffee, you walk a couple steps this way, you stop again. And what they found is really the number of steps you're taking in a row at most was like 4. That was kind of the most occurred in the entire data set. This, you know, the locations during the day where you're walking 60, 70 steps in a row and really just walking one bout at once were very minimal. And so one of the main takeaways that they figured out from kind of studying and tracking people in the daily world is that, I'll read this quote exactly. So gates of daily living probably involve short bouts of walking with a short number of steps in a row, with maneuverability and stability being more important to successful community mobility rather than walking fast, walking for long periods of time, or achieving energy efficient self-selected walking speed. So this really made us think a lot about kind of stability, maneuverability, agility, and how some of these things could potentially be target goals for an exoskeleton that we weren't really thinking about right now. So this is a relatively new area of research for the wearable robotics community. So my overall goal for my dissertation is to do exactly that, is to get exoskeletons and research how these potentially could help stability. You can think for healthy individuals, this might be things like people are working really demanding environments and they might have to think so much about the way that they're navigating an environment, but also there's huge applications here for people in different clinical populations that have balance impairments. So you can think older adults, people who've had a stroke, people who've had a partial spinal cord injury, peripheral neuropathy, all of these people that deal with falls as a major risk when they're kind of moving around their environment. This could be a potentially very promising application for exoskeletons in the future. So the way that we kind of think about this stuff in our lab, and this kind of sets up some of the areas that I'm working on for my PhD, is we kind of, in our lab, think about a 3-tiered control architecture. So high level control, you can kind of think, this is the context of how you're moving around. So we think about this as estimating kind of the state of the environment. Conventionally in our lab, this has been, are you walking? Are you running? Are you going up a ramp, down a ramp, upstairs, downstairs? Kind of where are you in your walking cycle exactly? And all of those things change exactly what your joints are doing at that point in time. So the way that your hip joint acts and applies torque to your body is very different if you're walking upstairs versus down a ramp. So traditionally, we've had to think about how do we change what we want an exoskeleton to do and how to have it help you if you're walking in kind of a different mode or a different environment. Next, kind of the mid-level control. This is actually determining what do we want to do with the torque that we can apply to your body with an exoskeleton. So if you're going upstairs, we can do a lot of different types of mid-level control algorithms. So impedance control, basically you can just make the exoskeleton feel like a spring. You can add a little bit of damping. So those can be implemented in a passive device too, but the benefit of doing this with an exoskeleton that has motors is, let's say we want the spring to be a different stiffness if you're walking upstairs versus downstairs. That's something that you can kind of make feel a little bit different with a motor instead of a passive actual spring on the exoskeleton. We can do things like base it on your biological joint moment. So if you're walking around, we can look at basically the torque that you're naturally using at your hip and just give you 10% of that. That's another way that we've thought about augmenting, especially when you're thinking about energy cost. We can do spline control, we can do bang bang control, we can do a lot of these different kind of mid-level control architectures. Basically, it's just how we decide what torque we're applying to your body. And then at the very low level, basically just correcting torque errors. So depending on what kind of motor we're using, we have to think about making sure that what we think we're sending to the motor is the torque that we're actually getting back from the motor. So there's some low level control that we have to deal with depending on the devices that we're using. So really what the focus of my PhD has been so far is kind of this top level. So how do we figure out what is going on with your body, if you're unstable, kind of what direction you're unstable. Some of these things that will help us determine how do we want to use an exoskeleton to correct for some of your instability. And the way that we really think about doing this in our lab is we take a very data-driven approach. So this is specifically on the Epic Lab side of things. You'll see a lot of machine learning stuff coming out of the lab with applications with kind of wearable sensors and biomechanics. And so we tend to collect these huge multimodal data sets where people are doing a ton of different activities, or in my case, losing their balance in a lot of different ways, and trying to figure out if there's kind of seamless, continuous ways that across all of those situations, we can kind of capture what your body's doing or capture something about the way you're moving around so that we can create some sort of exoskeleton controller that applies to all of those situations. We traditionally have in the past done some things with state machines, which is basically you chunk upstairs differently from downstairs versus up a ramp versus down a ramp. That can break down very quickly the second you're doing any activity that we don't have a little box for. So we're really moving towards trying to get everything in this big kind of continuous space where we don't have to worry about kind of those weird niche activities that kind of break the logic of the exoskeleton. So basically collect these huge multimodal data sets. I'll talk a little bit later about some of the machine learning approaches that we take. And then we're really trying to get biomechanical outcomes that we can use in real time to basically feed back to an exoskeleton and say, here's what they're doing. How should we apply torque to their body with a device? Cool. Feel free to stop me if there's any questions. Otherwise, I'll just keep going through. So the first question we really had, so stability was a very new application for our lab when I joined 4 years ago. So we really wanted to figure out how are humans responding to perturbations without any sort of assistance. And a perturbation I'll define quick as I have this video playing. So perturbation we think of as any kind of like environmental disturbance that disrupts your balance. So this you're seeing the way that we apply it in the lab, which is on this big moving platform. But perturbations you'll kind of experience in daily life is if you're walking down the aisle of a bus and all of a sudden they hit the brakes, if you don't see a curb coming and you accidentally step off the curb and didn't realize it was there and you kind of have that sudden change to the height of the ground, all of those different things that kind of disrupt your balance on a day-to-day basis are what we kind of think of as perturbations. So in our lab, we have this huge system. So this is a big Stewart platform, which is basically this massive platform can move in 6 degrees of freedom. And we have total control over this thing within reasonable extent. We wish we could tune the parameters a little bit more. But then we have a whole motion capture lab surrounded around this. So you guys might be familiar with a lot of the stuff that Natalia is working on setting up right now. So we have motion capture cameras, but we also have an instrumented treadmill there in the bottom where we can get forces and moments in all directions under your feet. And that way we can actually end up figuring out kind of what torques all of your joints are applying when you're doing these experiments.
Yes. Niche question. So when you're doing these perturbations, you're seeing your subject step onto 2 sides of the belt treadmill at once.
Yes.
How do you process that data? That sounds like such a pain.
this has been a big challenge. So the question here is, can they hear the questions online? Cool. So one of the big challenges is when you do inverse dynamics, which is basically the process of you just treat the human like a dynamical system in any sort of dynamics class, and you know where the forces are being applied to the body, and you can propagate that up and say, here's what's happening at the ankle, the knee, the hip. And so when you have someone cross over onto one force plate like this, now all of a sudden the force vector you're getting and the location that it's being applied to the person is somewhere between their 2 feet. So you don't actually know how it's divvied up between both feet. So very large question. There's also a lot of issues when you have this massive platform accelerating in space. F equals ma really comes into play. We get like 600 newtons in the direction that the platform is moving that thinks it's rating that's not actually from the person. So the easy answer to your question is we ignore double stance. We're working on a different solution using some fun like machine learning techniques to try to basically figure out when both your feet are on the ground and we don't know exactly where that force is being applied, seeing if we can kind of figure out how to split it out between the 2 feet.
Yeah, or instrumented insoles.
That's an in-depth conversation. If it's good enough to replace what we get from a force platform is a question mark. Not yet with insoles, exactly. So there's also devices you can just wear that are instrumented, like insoles that you can put in a shoe that can give you some of those forces instead. All right. So basically this experiment we ran, we wanted to figure out what are all of the different ways that we could potentially make someone unstable and really try to get a huge data set. So again, we could go for some of those continuous variables that maybe would let us kind of capture instability in a bunch of different ways and not have to deal with kind of those state machine type approaches that I was talking about earlier. So the first thing that we did is we took this platform and we moved it at 3 different magnitudes. So we displaced it basically 5, 10, and 15 centimeter displacements. That scales with velocity and acceleration as well. So they're kind of getting intense across all 3 of those measures of how the platform's moving. And we also moved it in 8 different directions. So we kind of did around the clock, so it's sliding under you, but no vertical height changes. That can be kind of weird when both your feet are on the same platform. It feels like you're in an elevator moving up. So it's not quite kind of pitching your body as much as it's like accelerating you into the ground. And then we also developed a closed loop control paradigm where basically we could track your walking cycle in real time. So exactly where you were in your walking cycle and then hit you with a perturbation at very specific times during your walking cycle. And that ended up actually being one of the most influential variables. So if you're here versus here when a perturbation starts, your reaction and balance are drastically different, even though the difference between here and here is about 200 milliseconds when you're walking. So it actually makes quite a big difference. So it's this same video. I'll just play this again. So we did this with 11 participants, might be doing some more. And we did just over 3,100 perturbations. And this was just over 10 hours of data. For the machine learning people in the room, our data set is just over 3 million data points. So that's kind of what we're working with on the machine learning side of things. And we might be scaling that up a little bit more depending on what algorithms we're using. Yeah.
I have one question. So the participants expected some perturbations in this case.
That's a great question. Yeah. Is that?
Yeah. So like, don't they change like behavior from normal state because they know that something will happen?
Yeah, that's a great question. So we do as much as we can on the experimental design side to inhibit that. So they don't know when exactly it's coming. So we've randomized the timing. They don't know which foot that they're going to get perturbed on, and they don't know which of these conditions are coming. So we kind of mix everything as much as possible. And there tends to be about 15 to 25 seconds between the perturbations. So they've usually gotten back to kind of normal steady state walking, but you're absolutely right. After they feel the first one, there is a little bit of adaptation in how they walk, depending on exactly how kind of conservative they're going to be with the way they're walking and how threatened they feel by the instability. So I've seen 1 or 2 studies where they had people come in, they put all of the sensors on them, they did 1 perturbation, and then they left. We probably don't have the time to do that because the setup for this experiment was 2 hours before we could actually collect data. But yeah, you're absolutely right. So one thing that probably another grad student will get to is we tried to also organize the study so we could see if they're getting better over the course of time. So There were 96 conditions between those ones that I showed. So we did each of the 96 in one session, and then they took a break, and then we did the 96 again, and then the 96 again. And one of the things that we have always been interested in looking at is exactly that. Like, are they figuring out some way to adapt that actually makes them better at responding to these? So yeah, definitely a very open question that hopefully I probably won't get to, but someone will get to at some point.
Cool, thanks.
Yeah. All right, so I'm gonna go over, this is just kind of one of the key balance metrics that we think about. This metric that I'm gonna talk about is called whole body angular momentum. If you guys are at all familiar with kind of the bipedal robotics community side of things, this tends to be some sort of common terminology, but you can think this is just the overall momentum of your body rotating about kind of the center or your center of mass. So this is just kind of one way that we measure balance in biomechanics. And this is whole body angular momentum in the sagittal plane, which is just looking at me from the side as I'm walking. And one of the things that we really just wanted to see is relative to steady state, which is kind of normal walking where you're not losing your balance, is that black line with kind of that gray standard deviation in the background. We just wanted to make sure we're really messing with this as much as we thought we were, and were we kind of knocking them off of that normal curve in a bunch of different ways to kind of get the variability that we were hoping for. And you can see just based on different directions that we're moving the platform, we kind of got a nice spread in the step that we perturb them on. So this is just one step. So from contact on this foot to contact on the next foot. And we were able to kind of knock them off of their typical trajectory. And then we even just kind of looked at the step after that, and you can see they're pretty unstable still 2 steps after the perturbation. And we still get this really nice spread depending on the direction. So this was good validation that we were getting the diversity of data that we were hoping for. And then we also looked at this in the frontal plane, or basically just looking at me from the front. Usually you kind of oscillate like this when you walk. And we also saw something similar here where you again get this nice spread of data depending on which direction you move them in. And then this one is kind of a little easier to imagine. So this is kind of a bird's eye view looking down at the ground at where people's feet are hitting. So you can imagine these are footprints, like let's say you were walking with chalk on your feet. So if this is where your foot was when we perturbed you, or kind of your foot was already on the ground when we started moving the platform, we were also getting them to really change kind of the way they were reacting to this perturbation. So this is the location of kind of where their heel came down on the next foot. So again, getting a nice diversity of reactions there. And then again, on the next step, we were still seeing, for some perturbations, people tended to be back to normal already by the end of that second step, but for others, they were still kind of spread out relative to what they do during normal walking. All right. And then one of the things we also wanted to look at is, I'll kind of go over some rough trends here, but we wanted to figure out, okay, we're using the magnitude of the perturbation, the timing of the perturbation, the direction to kind of influence how they're reacting. And we kind of wanted to figure out which ones are the most influential, or how are these variables actually affecting the way that someone is reacting to a perturbation. So what we basically did is we just kind of binned their responses between no responses like under 2 standard deviations. We didn't consider it extremely significant and something that we would view as a huge deviation in their reaction. And then we kind of binned it into small, medium, and large changes in their step placement, and then a fun little category that I'll talk about after this slide. So first, we looked at the magnitude of the perturbation, and this one was kind of our sanity check. So if we move the platform more at a higher acceleration, we should see a bigger reaction. That was kind of the one sanity check. So we saw here, basically, you can think the darker the colors in the pie chart are, the more that they're kind of up on the high reaction side of things. So, right, we saw on the step that we actually moved the platform on, greater magnitude caused greater reactions, good sanity check. Also on the step after that one, so this is just the step after the perturbed one, we also saw greater changes in their step placement. So this was our sanity check independent variable. Timing was an interesting one. So basically, the earlier you perturb them, you can think this is the longest amount of time before they put their foot down, we saw the greatest reaction. We basically think that's because if you're here and you're walking, you have the longest amount of time until you're able to put your foot down somewhere. So you're probably kind of accumulating instability because you have a kind of a long time before you can react to it. So their changes in step placement were a lot greater. But on the second one, we kind of saw it shift. And what we think is going on is there's a limit in kind of reaction time here. So it takes somewhere around 100 to 150 milliseconds for people to really move their limbs intentionally and consciously after some sort of disturbance. And this perturbation happens about 200 milliseconds before you put your foot down. So what we think is happening here is they couldn't really move their foot in time, so they kind of have to do it on the next step. And that's the reason you see that kind of shift where the later ones are bad in this step. All right, and the last one. This one's a little harder to visualize, but just think about the ones on the sides are ones that the platform's kind of moving back and forth sideways, and then the ones on the top and the bottom where it's kind of sliding forward and backwards. So if you're ever walking and someone pushes you forward, it's a lot easier to recover from that than if someone kind of knocks you to the side. So we saw some different trends here where if you're forced to take kind of a widening step or a narrowing step, those cause a much greater change in where you put your feet than ones that go forward and backwards. And those trends were really the same in the second one. But
One question. I mean, interesting type of the people participating in the experiments. It's just like a normal people, it's the young people, is it a professional sportsman, maybe dancer, or maybe the people with the injury?
yeah, there's a lot of awesome questions in that. So who's participating? Right now, you'll see it's like 24 years plus or minus something. That's because it's mostly young grad students. The question about whether or not it's athletes is actually an interesting one. We have a collaborator who studied kind of normal young adults versus ballerinas and their balance. So some of these activities that you think might heavily influence how used people are to losing their balance and recovering, or if they're trained in a specific way. So that's definitely something that has been in the back of our mind, is if there's certain people that might be trained to be better at these. And we've also collected this data set. I'm not going to talk about it today, but with people who have a stroke, so older adults who have some sort of balance impairment, and that the results look very different in comparison. So these, I would say, are young, healthy adults that are pretty capable in terms of kind of rejecting the perturbation and not falling down. Cool. Okay, so the fun one that popped out of this was this strategy that we were not expecting, which is this jump category that I didn't talk about earlier. So basically what this is there was at some point during their recovery strategy time where they actually lost all contact with the ground. So they had an aerial phase, or they jumped at some point in the air. And I'll show a video. It goes kind of fast, but watch a couple steps in. You'll see she gets knocked to the side. Her legs kind of get tangled up and she ends up kind of hopping back to the middle of the treadmill. Play that one more time. And so we saw this strategy a couple times during this study. And what we figured out is people's legs were kind of getting tangled when they had to execute a certain maneuver to recover their balance. And so one day, this is a lab that works next to us, led by Dr. Ye Zhao, and they were interested in doing some stability experiments with their robot. And I said, hey, we've been seeing this strategy happen with humans. I don't really see robots jump a lot when they're walking around. Like, what does this robot do when you put it in the situation where its legs kind of get tangled up? And so we just put the robot on, tried it, and it turns out it doesn't have a way to compensate for this. So I'll play that one more time. You can see feet cross over, and the underlying algorithm, it turns out, that they were using did not have a way to compensate for this. So this is spun out into kind of a fun side project with them, where we're potentially going to use some kind of human-inspired strategies to inform what this robot is doing. So going back to the number of jumps we saw in the study, to recap, we had just over 3,100 perturbations in this study. We saw 27 jumps. So originally we just thought, okay, this is some weird niche case that something weird happened, and we can probably just toss this out and not worry about it, and just acknowledge that this happened and we're excluding this data. But it turns out when we looked a little bit closer at it, that only 8 of the 96 conditions that we were testing ever had this happen. And if you look a little bit closer, these are just the distributions of those different conditions. And we saw, we were like, okay, it doesn't seem like this is a coincidence that it's happening when sometimes, 10 to 30% of the reactions across all of our participants were this jump strategy. So we started looking a little bit closer at it. And what we kind of figured out is that the commonality is you have to hit them with the perfect direction and the perfect time during their walking cycle to get this to happen. And it was all conditions where they had to take a crossover step, but their stance limb, or the limb that was on the ground, was in the path of where their other limb wanted to go. So the cool kind of commonality with other perturbation research is a lot of people do stumble recovery studies where there's a block on the ground and you trip on it and you have to recover. But this is a kind of a rare case where the thing you're stumbling on is also yourself. So you can't just avoid that obstacle and completely change what you're doing, because the foot that's on the ground is your only point of contact with the ground at that point. So we wanted to kind of formalize this and see if kind of these qualitative things that we were observing were taking place. So I had a really phenomenal undergrad named Viva Iyer who's helping me work on this, and we're hopefully going to be putting out a paper later this summer. And so the first possible cause we wanted to look at is if there's a projected collision between where your swing limb, or the limb that's in the air, wants to go and the foot that's on the ground. Is that what actually is causing these? So we kind of formalized this by looking at the instantaneous velocity vector of your foot as it was swinging through the air, and if it was going to collide with your limb that was on the ground. And then we kind of thought that's the one that would require you to do something weird, because you actually have a physical collision in the environment. And our kind of secondary hypothesis was maybe the step that you need to take is too narrow, so too much of a crossover step for you to actually be able to execute that. So you kind of are limited in how much you can cross your two legs over. So we also fit a linear model that had been previously published to say, if they hadn't hit this jump situation, where would they wanted to place their foot? Was that actually achievable? And then we looked at 3 different jump strategies that were used. These are really hard to show diagrams for, so I'm going to act them out a little bit. A foot replacement is basically this foot's on the ground and you kind of jump and put the other foot down in the exact same spot and keep walking. A leap was just kind of a normal step, but there was some sort of aerial or jump phase in the middle. And then a skip is we actually saw people that were falling to the outside of their body, kind of like hop laterally on their foot and continue to walk. So these were all strategies that we had kind of qualitatively observed. And we wanted to figure out, is the way that people are reacting to these situations correlated? So do people kind of execute this recovery strategy in the same way? So we saw is if you were projected to collide, which was, yeah.
Sorry. So why do you think like not all or only 30% of the people need to jump in these cases? Is it because like the timing is not perfect, or is that they're, I don't know, they're just not, they're not gliding at wider steps?
This is a really good question. We actually have just collected a follow-up study, and there is so much participant-specific preference with how they handle this situation. And exactly why is a hard question to ask, or a hard question to answer. But we are definitely seeing in the follow-up study some participants jumping like over 50% of the time and some not at all. But we are kind of seeing this emergence of different strategies where, so let's say you need to take a crossover step. Some people are like pitching their torso this way so their leg kind of comes around instead of having to go straight through. And I don't know if it's that other people just haven't figured out that that's an option, or if maybe they just have a preference for a different one. Also, we've noticed some rough correlations depending on the way people are built and their height and things like that, that affect their range of motion, kind of what they're used to doing. And then a last really challenging question to answer is if you are 6'5" and 225 pounds versus someone who's 5'1" and 130 pounds, is this putting you in the exact same situation? So we are starting to also look at like, how is this affecting different people differently? And is there a chance we're actually challenging some people more than others by fixing the movement of this platform across all the people?
I would also expect gender-specific differences because women tend to have their center of mass distributed differently than men do.
Yeah.
Different centers of gravity.
Yeah, absolutely. Cool, great question. So basically what we saw is this projected collision. We analyzed 26 of the jump trials. 22 of them were this projected collision situation. And of the other ones that were remaining, 2 of them we classified as the too narrow, and then the other 2 we're not sure exactly what was going on quite yet. But what we did see is if you put people in this projected collision situation, it seems like they often did the foot replacement strategy, which is where they kind of switched their feet with a little bit of a jump in the middle. The other 2, I won't make any conclusions based off of these because the numbers are too small, but we did do a follow-up study. I'll just play one here. Forgot to cut the sound on this one. So you can see that he hits a little bit of a foot collision and kind of does the foot switch there. So we did a follow-up study where we cranked up the magnitude even a little bit higher to make these more challenging, and we targeted 50% of all of the conditions that we applied were these kind of like jump-inducing situations. So I collected this 2 weeks ago, so stay tuned for what the results are from this one. All right, so that's going to be it on kind of the pure biomechanics side of things. The next chunk of what we're really looking into is getting to that kind of high-level control problem of estimating the state of the individual using wearable sensors and machine learning. So the way that we kind of think about this in our lab is we have wearable sensors in a bunch of different contexts that we can get from people. So often we have some different wearable sensors on an exoskeleton that someone wears. It's typical for us to use IMUs, which are accelerometers and gyroscopes, on kind of the different segments of your body that the exoskeleton is attaching to. And then we also have encoders in the actuators, so we can get the angle and angular velocity of the different joints that are moving that the exoskeleton is attached to. We also have a way of taking just our pure biomechanics data and in our model saying if we had put an IMU at this location, what would the results be? And so that's a really nice way that we can test some of these ideas without having to collect an entirely new data set with someone wearing a different exoskeleton. And then the machine learning models that we use in the middle have really varied with the lab over time. So we always try to start with simpler models, make sure that we're seeing what we expect, make sure that more complex models are necessary before we really scale things up. And we've gone through a lot of different possible options, but the kind of favorite in the lab right now is called a temporal convolutional network, or a TCN, which is a form of a deep learning neural net that we have figured out through a lot of experimenting in our labs. Really, really good for this data where you kind of have time history of data and time actually matters. And then what we're usually trying to do is predict some sort of outcome of what's happening to the human. So in my case, we've thought about whole body angular momentum, which is that balance metric that we talked about, where they're going to put their feet, what's kind of happening to their center of mass, or kind of the point that we use to generalize what's happening to their balance. And for a lot of different reasons. You can think if we, see a change in your whole body angular momentum, that's maybe when we have the exoskeleton to kick on and do something different for your balance. We can also think about using this if we ever want to collect data outside of the lab in a more realistic environment, not just on that perturbation platform. We could get some of these outcomes in real time and not need all of our crazy lab equipment. So there's a lot of possible different use cases for what we would do with these outputs. So I'm kind of going to go over why the balance project has been challenging relative to some of the other ML applications that we've been focusing on in our lab. So first, from an outcomes perspective, we're thinking mostly about these IMUs, which you can think of largely mechanical sensors. We're getting linear accelerations and angular velocities. So kind of the easiest case scenario is, imagine we're trying to get your center of mass, which is somewhere around your belly button typically. We're trying to get the velocity of your center of mass. And we have this sensor directly on your center of mass. That's kind of easiest case scenario because the mapping between the sensor and our output is pretty simple. Then we can get to these more challenging things like your whole body kinematics. So maybe we only have sensors at your torso and your thighs because we're using a hip exoskeleton, but we want to know where your feet are in space. Something like that where it's a little bit more of an abstract mapping between the sensors that we have and what your actual outcome is going to be. And then the most challenging one is you add forces and moments. So these things that are not in any way directly measured by the sensor, where the machine learning model might have to learn a little bit about the inertia or the weight of your body segments, the way that you would be applying forces to the ground, things like that. So it's a lot more abstracted from exactly what we're measuring. So that's kind of the increase in challenge with our outcome. In terms of the context, this is typically what steady state data looks like for almost any variable that we look at during walking. It's cyclic, it's nice, people are pretty precise and hit the same magnitudes every time. So when you have a very consistent output and a very consistent input, figuring out the mapping between those two tends to be a little bit easier. But when we mess with someone's balance and all of a sudden push them off track, you get these really transient and sudden changes into some of the outcomes that we're looking at. And especially a big challenge for us is this idea of kind of data imbalance. So we have a lot of normal walking motion data, but it's hard to get a ton of these little changes without running crazy, crazy long experiments. And then the last one is kind of when we're estimating whatever our outcome is. So typically we think about some sort of input data. So you can think about this as a wearable sensor that we're looking at over time. And we have some sort of time history of this data, and you can think this side is right now and this is into the past. So the kind of standard case is we're trying to estimate right now with the sensors we have right now and some previous time history. The slightly easier case is we're trying to estimate something that previously happened. So we have a little bit of data before and after when we're actually trying to estimate some sort of outcome like your center of mass, speed, or something like that. And then the challenging case that we're potentially interested in is actually predicting into the future. So if we know what's happening right now, can we predict what the state of your body or your biomechanics are going to be in 200 milliseconds into the future, or even further, depending on what our application is. And one of the reasons we might want to do that is exoskeletons, right? You might need some time to apply torque to actually get the exoskeleton to move your body. So if we can be a little bit more proactive rather than reactive, that might help with some of our control algorithms. So the first thing that we tried to really push the boundary here was to look at the relationship between your center of mass and your center of pressure. So center of mass in the kind of global state is just how much your body's moving. But if we want to kind of understand it in the context of how you're moving relative to where your foot is on the ground, gives us a little bit more of a local reference frame and kind of how your own body is changing. So we think about like an inverted pendulum model so that your point of contact on the ground and your center of mass is moving relative to wherever you are. And I have a phenomenal undergraduate student who's now heading to do her master's at Northwestern that worked on this for like the last 3 years with me. And I'll pitch some of her work in a second. So we used this big data set that we collected. And then we kind of defined, right, so your center of mass is somewhere here around your belly button. And then we could look at the center of pressure between both of your feet over time. So we basically looked at, in again, this plane, so kind of moving in the direction of walking, and then also looking at someone from the front, so moving side to side. And we looked at the position and velocity to see how well we could estimate these with our wearable sensors. So the first question we want to ask is, which sensor locations are required? So the ideal scenario is we don't want to have to put an IMU on every single segment of your body. Getting someone to wake up and put that on so you can track them in the real world is going to be a lot more difficult than if it's already in something they're going to wear and they can just, let's say, pull on an exoskeleton, 25 years into the future, maybe when we're actually wearing these on a day-to-day basis, and the sensor's already in there. But that also makes it a much more challenging problem. The fewer sensors you have, the less you know about the mechanics of the way that their body is moving. So we wanted to know, can we get away with sensors that are already on these devices that we're wearing and not have to put on anything onto the person's body in addition to the exoskeleton they're already having to strap on and put on their body? So we looked at a bunch of different combinations. Basically, you can think if we have a hip exoskeleton with actuators on your hips, we typically attach the segment above and below that. So that would be the torso and the thighs. If it's the knee, we attach to the thighs and the shin. And if it's the ankle, we attach to the shin and the foot. And then we wanted to compare this to the case where we had all sensors, which is basically torso and down. We had a sensor on every segment. So that's kind of our best case scenario at this point. And we basically found is steady state. So again, this easy cyclic kind of normal case that we were expecting to be a little bit easier. We were getting, R squared values into the upper, 0.97, 0.98. So these were pretty phenomenal in terms of how well we were able to match our outcome with the machine learning model. And to clarify, we have the actual measurement from our gold standard biomechanics data, and then we're comparing it to the machine learning output. If we look at the perturbed data, so we're looking just the second after the perturbation, you can definitely see we get a decrease in accuracy, but we're still hitting above a 0.9 R squared value, which meant some of our trends were showing up pretty well in the machine learning side of things. And this is still viewed as a pretty strong R squared value for some of the ML models that we use in our lab. So it's definitely more challenging, but what was one of the really cool findings is wearing all of the sensors, which is the dark gray bar here, didn't seem to add much in comparison to just using sensors on the exoskeleton. So that was a very promising sign that we could potentially get away with just sensors that someone would already be wearing. And I should say I'm only showing one of these outputs because it just adds up to be a lot of bar graphs, but I have those if anyone's curious or has any questions about them. So the next thing we wanted to look at, again, we're comparing steady state and perturbed, so kind of our easy case and our more challenging case. And if we basically look into the past, so that case where we're predicting data that we already have stuff before and after, versus into the future up to 150 milliseconds, what is actually the effect on the accuracy of these models? And you can see with steady state data, again, everything's still staying pretty strong. So even going into the future, it still did pretty well. And you can think, right, if you're walking normally, if you're hitting kind of the exact same biomechanics every time, the same step placement, if I know what's happening right here, probably know what's going to happen when your foot's coming down, 150 to 200 milliseconds later. When we do it during perturbed walking, so the second after the perturbation, you can see that we definitely get, it's a lot bigger challenge for the model to predict into the future when you're kind of in this transient, changing, very sudden change to your biomechanics portion of the data. So it gets harder and harder to look into the future. But again, up to 150 milliseconds, we were still getting R-squared values above 0.9, and this is just using hip exoskeleton sensors. This is not necessarily even using all the sensors. So still pretty promising, even though we get a little bit of diminishing return when we predict into the future. So a way that we would think about using this is if something's going to be happening to your mechanics of your body 150 milliseconds into the future, we can actually do something with the exoskeleton now, so that's corrected by the time you get there, or we can be a little bit more proactive in addressing exactly what's going on. And then this is Courtney's project. She's working on a first author paper for this right now, which is really exciting. And she wanted to see if we could use a similar model to estimate the whole body angular momentum balance biomechanical variable that I mentioned in the biomechanics section. And we wanted to, again, figure out how many sensors are needed. This one is a little bit more, it's capturing your arms and your legs and everything about your body. So we thought we might need a few more sensors. But we've also worked on some really cool adaptations to our model where we have this big deep learning model that we're passing all of our data through, but we have like 11-second trials. The perturbation happens around 4.5 seconds. They're unstable for 1 or 2 seconds. So we really have a lot of normal walking data and a little bit of perturbation data. So what she did is we actually went in, trained the entire model, locked some of the layers in our machine learning model, and just passed back kind of like a perturbation heavy data set to see if we could tune it a little bit more to the perturbation without sacrificing too much on the normal walking side of things. So hopefully just improving the perturbation part. And you can see the output of the model is pretty good. So we're hitting like just over a 0.95 R-squared value. So the black is our actual gold standard curve from our biomechanics data, and the light purple is what the model's output is right now. So you can see we're capturing it pretty well. You get right after the perturbation here, you get a little bit of increase in error where it's not perfectly tracking, which is kind of where we expect the most challenging portion of this problem to be. Okay. And then the last thing we're kind of thinking about from an ML perspective is how do we detect a perturbation? So let's say we want someone to have kind of that energy augmentation mode when they're kind of walking around normally. And then when they start to lose their balance, we kind of kick in balance augmentation mode. So we can kind of get a dual benefit to these exoskeletons. We want to figure out how fast can we detect exactly when a perturbation is happening. So this was led by Reese Peterson, who was a master's student I worked with while he was in the lab. And we did a slip perturbation study where basically you're kind of taking one of these belts and moving it under the person's foot, and it kind of feels like you're slipping on ice. Either we have 2 different cases. An early slip is right when your foot comes down. It's if your foot kind of like slid in front of you, like you stepped on a block of ice. And a late one is as you're pushing off, when you would kind of lose friction when you're pushing off behind you. And what he did was compare a few different machine learning models. We looked at LDA XGBoost, which is gradient boosted decision trees, as well as a convolutional neural network. And we tried to figure out how good are these models at kind of reducing the amount of time we need to actually detect the perturbation. And this is just the 2 different perturbation conditions that we looked at. So we were able to get down to anywhere from 150 to 250 milliseconds. And our goal was to kind of beat what was currently out there and see if we could get something that was faster by investigating some of these different models. So Reese kind of defined this as the goal zone, which was more accurate than things that had been previously published, but also quicker detection time. And what was cool is these 2 here are the outputs from his model. So he was able to kind of get both the early and the late slip perturbations in that region that we were targeting. All right. Okay, so that's kind of it on the ML side of things, and then I'll briefly highlight just what the current state of our exoskeleton is. So when I entered the lab, we did not have an exoskeleton that was kind of suited for balance augmentation. If you guys remember, kind of those side-to-side perturbations tend to be a little bit more challenging, and because we're investigating walking a lot, they tend to just be ones that augment from the side. So motors on the sides that kind of help your limbs go back and forth. But we really needed something that helped with kind of the frontal plane or from the front view, move your legs in and out too, because those were where we saw perturbations be a lot more challenging. So this is an exoskeleton that we designed along with Max Anderson, who was again an MS student that I worked with while he was in the lab. And you can see this is wearing the current version of the exoskeleton. And the kind of new innovation here is you can see you kind of wear this like a backpack. And you have motors that sit behind your hips. So those kind of help with the in and out motion, as well as motors on the sides. So we can still work on moving your legs backward and forward. And then we kind of attach these over here, you can see in series. So we're able to just connect to your leg once, but have both of these actuators acting on the same leg. So in terms of what we have on here, we just rebuilt this for a new set of actuators. So these specs are going to change a little bit. But we're kind of operating somewhere in the region where we can apply somewhere between like 18 and 26 Newton meters of torque to your hip joints, which is a portion of what you usually do when you're walking around, but it tends to be kind of pushing the limit in terms of what people are comfortable with if they are kind of healthy, able-bodied people. People don't like to relinquish 100% of their hip torque to a device. We put IMUs kind of here where we attach to your legs, as well as one on the torso. And we also have encoders, which are those angle and angular velocity sensors that we have at the different joints. So we basically know your hip motion thanks to those actuators. And then the last thing that we have is we use a NVIDIA Jetson Nano, which is basically a really capable computer that we can mount on the device. I'll show a picture here. So the Jetson Nano is actually smaller than the battery that we need to run the actuators, but it's a powerful enough computer where we can run machine learning models in real time when we're running these experiments and turn things around pretty quickly. And then we actually just upgraded. I don't know if anyone is on this side of things, but NVIDIA just released a new Nano called an Orin, which let us get rid of a couple of the other components here. So we just upgraded the system about a week before I left. And that's both a faster computer and lets us get rid of this little low-level teensy controller that we had on there. So, last step and kind of the remainder of my PhD, I have about a year left, I hope, plan. And there's a lot of different controllers that we've talked about that we're kind of narrowing down right now. So the first one is just simple model-based controllers. If we know something about your center of mass and where your feet usually go, can we drive you to maybe a better step placement? Or maybe if you don't have enough reaction time, like I mentioned earlier, maybe we can kind of speed up, kind of where you're able to put your feet with the exoskeleton. So in that kind of situation I mentioned where maybe they don't get their foot quite where they want to because they didn't have enough time, we might just be able to say, here's where your foot should go based on your center of mass and have the exoskeleton react a little bit quicker. We've also looked at taking some strategies from kind of the bipedal robotics world. So a lot of strategies that we've seen, they kind of drive you to recover in a single step. So you can think one step and you've dissipated all of your instability. And we don't see humans do that. We see kind of this like multi-step recovery where it takes a couple seconds to get back to steady state walking. So we've thought about potentially pulling some of the knowledge from that side of the field and applying it to exoskeletons. And then the last one, which is obviously going to happen because of all the support work that we're going to be doing, is exploring the ways that we can drive these exoskeletons with machine learning. So collecting some wearable sensors, passing it through a model that we've trained, and get real-time, feedback about what type of assistance we want to pass back into the exoskeleton and explore what that looks like. There's a lot of tuning that comes in here, how much torque you want to be giving them, exactly the timing at which you're applying it. There's usually a lot of piloting that goes into these experiments as well. All right, that should be it. So I work in two really great labs. I thought we had big labs until I got to hear about the groups that are here. So we have quite a few grad students, and as you guys know, it's fun to have a lot of different people around working on different things. Like I mentioned, the top lab works a lot on physiology and kind of that side of wearable robotics. The bottom lab works a little bit more on the intelligence side of things. And then I think I highlighted most of these collaborators as I was going through, and then We also have a really fantastic undergraduate and master's research program. So I've gotten to work with a lot of really phenomenal students do that. So thank you. Happy to take more questions.
And people online should be able to unmute themselves and ask a question. They can raise their hand.
Yeah. So I was really curious about your multimodal data set because it looked like on your treadmill platform you were using cameras and a bunch of different things. I'm wondering what time scales you're collecting data at and how you synchronize your different streams.
Yeah, great question. So all of our analog channels, so we have everything coming from the force plates that are under the person. And then something I actually didn't highlight is we have muscle activation sensors called EMGs on 16 different muscles in their lower body. And 8 of those also have IMUs in them. All of that data we're collecting at 2000 hertz. And then all of the motion capture data, so the markers and stuff that we're getting from around them are 100 hertz. So luckily we have it set up where all of them are being triggered to collect at once. One of the challenging things that is once we had an exoskeleton in there, now you have a completely separate device that you have to synchronize with all of that data. So we tend to use kind of high-low triggers to make sure that everything starts and stops collecting at the same time. And then just make sure we're getting, you know, timestamps and everything like that so we can make sure that we're collecting at the frequency that we expect. If it is something that's, you know, the motion capture system, it's taking care of all of the frequency at which we're collecting and controlling that. But sometimes we have to be a bit more conscious on our other devices and adding clocks and timers and making sure that we're collecting at a set frequency. I have dealt with a project where they're not synchronized, and that's a fun little experiment that you can do at the beginning of analysis. Yeah.
Actually, for the previous slide, when you show there is typically people need more than 1 steps for the recovering, right? And you explain the reference would be 1.
Yeah.
Only, like, I don't know, goal in the future. So as far as I understood, the exoskeleton is something which correct or help to make the task easily. And is there any plans in the project, or it's strategically correct, try to adjust the human motions to reduce the steps? Like, so the person would tend to make like a 10 or 5 steps to recovering, and the exoskeleton would try to fix it to minimize it to 1.
Yeah, that's a really great question. So one of the things that we've been really curious about, especially since we're working with healthy young people right now, is what is their objective function or cost function? So what is making them not choose the single step recovery? Because what I actually didn't mention is we're not seeing people miss this because they don't quite get their step wide enough. We're actually seeing people go wider than they need to. So they're kind of overshooting the target. So one of the questions we're really interested in, and I don't know if we have immediate plans to figure out exactly what it is there's got to be something else that they're weighing that is more important than correcting their instability quickly. We think that there might be some concepts like robustness. So people are a lot more comfortable taking a wider step than they are a narrowing step. This tends to feel a little bit more stable. You can move your leg around a lot more in the widening direction than you can the narrowing direction. So we think one of the reasons people might be doing this is they're setting themselves up to kind of have more options in the next step rather than, you know, maybe if they do a single step and there's a little bit of error, they might force themselves into one of those more uncomfortable or less feasible strategies. And I think where your question will really come in is we're starting to investigate different clinical populations of people that we would think are kind of like suboptimal at recovering their balance. And we're trying to figure out, do they have the same overcompensation mechanism, or are maybe they have a lot more variability, like because of reduced sensing or noisier sensing in their body, they actually aren't putting their foot exactly where they think they are. And so that is where I think there's definitely some promise in kind of pushing them towards a less, like, fewer step recovery strategy for sure. Yeah.
One more question and we'll break for lunch. Hey.
Yeah.
I have a question about the machine learning part where you do the exoskeleton control. Your data sets or the evaluation that you showed, is that on like holdout data from the participants that were generally also included in training, or on like completely new people that haven't been included in the training set?
Yeah, so when we're validating these models, we do, so let's say we have 11 participants in my case, we do leave one out kind of training of the model with 10 of them, and then we do the validation on a held out person. I will say there's still some, right, so let's say we're tuning the hyperparameters of our model or exactly how we're doing it. Those subjects are still in the data sets, even though they're being held out to validate what the other 10 are doing. So essentially the way we do it is if we're training, like, let's say the hyperparameters of one of these deep learning models, is we'll keep, 10 that we're actively training on. So we'll do 9, hold out 1. That'll be kind of the way that we'll tune all of those hyperparameters. And then we're using the hold one out to say, this is the actual accuracy of this model we just trained. But then, right, we're saying, here's the hyperparameters we tested. Here's all the hold one out participants. So at the end of the day, the way that we're choosing the hyperparameters still do encapsulate all of the subjects. But I will say when we deploy this offline, or when we're testing this offline, that's the way that we tend to go about training the models. When we actually use them, it most of the time tends to be new participants. So when we're actually using the models in real time for exoskeleton experiments, they are true hold one subject out users of the machine learning model.
And a follow-up question, because before you said that you're also collecting data somehow to be independent of the exact exoskeleton hardware, but I guess you would have to recollect the data sets every time you change, I don't know, like things on the exoskeleton, because they would maybe change the center of mass of the person then, or how things interact, right?
Yeah, exactly. So there's a couple, so the way that we're doing is we're taking biomechanics data sets, and we're saying, okay, if we had sensors here and here, what are the theoretical IMU signals that we would get? And we can do our best to match, like, here's where the exoskeleton would contact the person, put them in the right location, but there's still kind of best case scenario. So those sensors that we're generating offline, they kind of assume, right, that the sensor is rigidly attached to your skeleton. And when you put this on an actual exo, not only is it on the device, which can move around relative to your body, they're not perfectly coupled, the exoskeleton and the person, but you also have things like soft tissue noise, where you step down and your tissue can move a little bit. So we are working on some solutions around this, putting the sensors closer to the person, some different techniques to better introduce noise into those like ideal sensors that will make it easier to translate them onto our devices. But yeah, as of now, we at least have to collect some training data from the exoskeleton as well.
Great, let's thank Jay one more time.
Thank you.